Okay, here's a quick recap of what you did in the first computing session held before Student Development Week. And you see here we're starting with the template, which has in the columns, we've got some variables that we need to keep track of over time. And in the yellow box here, we've got various parameters that are useful for this simulation. Okay, so the first thing we'll do in column A is we'll populate the time, and we're going to use a time step of 0.1. So in this box, we can type the formula. This value is equal to the previous value plus the time step, which is this value here, 0.1. So if I click on that, that gives me the cell reference N4. And if I hit F4 after that, that puts dollar signs on that cell reference, which makes that an absolute reference. Hit return, and there that gives me 0.1, as you'd expect. Then I can drag down this formula, and that will populate this column of values. So I'll drag it down to 3 seconds. Okay, so now we need to start sort of working from the right. So not in column H. We're going to ignore these forces for now and the rocket mass. We're just going to look at these columns F and G, which is the acceleration on the rocket. And if you remember, we're just going to consider initially the coast phase, i.e. time after 0.8 seconds. And the acceleration in the x direction after 0.8 seconds or 0.9 seconds onwards is equal to 0. If I drag down 1 0, it'll probably count up, but if I drag down 2 zeros, that'll make all this column equal to 0. And the acceleration in the y direction, if you remember, was equal to minus the gravitational field strength. So I'm putting in a formula here, E is equal to minus the gravitational field strength, which is this value here, 9.81 meters per second squared. And again, after I've entered, clicked on M4 to get the cell reference, if I hit F4, that makes that a absolute cell reference. So all these values will be 9.81. When I drag it down, it will always refer to M4 because I've got the dollar signs there. So if you see, if I click on here, I've got that's equal to M4 minus M4. Okay, so we've got the acceleration set up. Now we need to calculate the velocities. Okay, and now we're going to assume that at the end of the start of the coast phase, the velocity is a certain value, and the coordinates, the x and y value of the rocket, are a certain value. So let's type in here 0.9 seconds. Let's say that the 10 meters, the height is 10 meters. Let's assume here that the velocity, total velocity is equal to, let's say, 15 meters per second, and the angle is equal to 45 degrees. Okay. So we can say here this velocity is equal to 15 times cos this angle here, L4, which is 45 degrees in radians. Make it an absolute reference. Actually, I don't need to make that an absolute reference. Make that equal to this value. And I can put in here the y velocity is equal to 15 times sine of 10. Okay. So these two values now refer to this angle. Actually, I don't think this angle is 45 degrees. It looks like it's 60 degrees. So the formula given here for converting degrees into radians, you times by pi and divide by 180. So if I make that 45 degrees, the x and y velocities become equal. Okay, so the final job now is to put the update formula in for the velocity in the x and y directions. So the velocity at this point, the velocity in the x direction is equal to the previous velocity times by the time difference times by the acceleration. So let's work on the y velocity at 1 second. That's equal to this value plus acceleration over the previous interval, this value, times by the time difference between these 2 points. So this value minus this value ends up being 0.1 of a second. So that's correct. The velocity, the acceleration is negative, the velocity is decreased a bit. So I can drag this down. Actually, I won't drag it down yet. I'll do the same for the x velocity. That's equal to the x velocity at the previous time plus the average acceleration in the x direction, which happens to be 0, times the time difference, this 12 minus A11. Now I can select both those cells, and that velocity is unchanged. So now I can select both those cells and drag them both down to give me my velocities up to 3 seconds. And you can see here that the y velocity goes negative, the x velocity is unchanged. Now I can write in the same update formula, same kind of update formula for my distances, just the same way. So I can say here that the x coordinate at this point is equal to the previous x coordinate plus the velocity at the previous point. We also have to refer to the previous point. Times by difference in time here. So A12 minus A11. That's my x direction, and I can do the same for my y direction. Actually, this is quite a useful thing to know. Here I've got a formula that is referring to this cell and these two cells. If I drag it across, I'll get the same formula applying to this cell, but I don't want the references into the A column to change. So what I can do is I can put a dollar sign in before the A. So this dollar sign before the A means use that cell value, but when you drag it across, keep the A's as A's. So now if I drag this across, I get the formula that I'm looking for. Okay, you can see it's very slightly different number because the velocity is very slightly different. Okay, so I'm very close to being able to plot the profile for the projectile or coast phase of this rocket. I can drag these two down, and this is telling me how my x and y coordinates are changing over time. So you can see here that the rocket's reached its peak height after about two seconds, and then it's starting to drop again. So now I can finally plot these values in a graph. So if I select both the columns and go insert graph, I can choose an XY scatter chart, and that gives me the trajectory. I've got height y plotted against x, and this looks the right kind of shape.